we want in a specific location. So the first thing we'll need if we want to have leaves falling from our trees is to know where to spawn these particles from. So to do this, we need to figure out where our trees are and then kind of create a hitbox to spawn our leaves from. And as always with Pygame, you're pretty much doing this all yourself. So we'll have to create all of the code for generating that area and figuring out which locations can spawn leaves based on the areas that we have and stuff like that. So let's get into it. So in order to get the position of our trees, I think it's best to go to the tile map, and we'll add a new function here that can be used for a lot of things. So let's call our function extract self, and it'll take the argument ID pairs, and then keep equals false. So what this function will do is it will take a list of ID pairs. So this is, if you remember, our tiles are in a like tile type format along with a variant. So it's type and variant, and those go together to uniquely identify the tile type. So that's what I'm referring to when I say ID pairs. More specifically, an ID pair is one of those two combined. Now the ID pairs is a list of those, and we'll check if a tile is in that list, and if it is, then we can return it. So what this function will do is it will take a bunch of types of tiles that we're looking for and tell us where they are and give us information about them in our map. And then if we want, is what this keep variable is for, we can have them removed from the map. So we're not going to need that yet because we do want to leave the trees hanging around in the map, but later when we do some other stuff, we might want to get rid of things. For example, if it's an entity spawn location, we might want to remove that from the map and then create an entity. All right, so to do this, let's create a list and call it matches, and then we can iterate over our tiles in our off-grid tiles. Let's do this one first because it's easier. And then the reason we're copying here is because we might want to delete from this list if we're not keeping. So we'll do if, and we'll make the tuple here for the ID pair, tile type, tile variant in ID pairs. That means that we've found one of the ID pairs that we're looking for. Then we'll do matches.append, and then we'll say tile.copy. So just give it the tile information. All right, now if we're not keeping our tile, then we want to remove it from our off-grid tiles. So that's pretty much the logic for that. Just look for the match, add it to the results, remove it if we don't want to keep it. And then we got to do the same thing for the tile map. So we go through the locations, and then we say tile equals self.tile map location, and then we do the match. So tile type, tile variant in ID pairs, matches.append, and then just another tile.copy. And then this is a little bit different. We'll have to do matches -1 position equals matches -1 position dot copy. So what we're doing here is we're going to change this position attribute, or not attribute, it's actually a key value pair in the tile dictionary, but we're changing the position for the tile that we're referencing because we want it to be in pixels. If you remember, the tile map is in tile coordinates for the grid, not in pixels. So we want to convert that. So to do that, we'll do matches -1 position 0 multiply, and we do self.tile size, typos. All right, and then we do that for the y-axis as well. So that gives us the pixel coordinates for our position. The reason why we do copy here is the same as up here. We want to have a copy of the tile. We don't want to be working with the exact same thing. And then over here we copy again because copy is just surface level. If there's a list nested inside of something, it won't actually copy that. It'll have the same reference. So this is just making sure it's clean. There's a function called deep copy that we could have used that will do basically these two things in one line, but I don't want to really get into that. So basically we're just making a clean copy of the tile data, because what would happen if we didn't is if we modified that tile data after getting the results, it would modify the actual tile in the tile map when we don't want that. And then, like I said, we're converting it to pixels. So now we can do the if not keep. We do del self.tile map location, and then we can return our matches. So now that we have our function here, we can grab this and we can go over to the game, and then we can say print self.tilemap and then we extract, and then for our ID pairs, we'll use a list with just the single pair of large decor 2. So if we wanted to get another type of decor, we could just do like this and say 1, but this will work for now. So we say large decor 2, and that will just match with this one tile, and then it'll give us all of this result. So we want keep to be true, because we don't want to remove the trees, and then that will give us the results of all of our matches here. So I run that, and then we can look down here and we see type large decor variant 2, and then here's the position we're looking for. So it's got all of this useful data, and then from this we can figure out where we can spawn our leaves. So I'm going to use a bit of a hack here. There are better ways to do this that are more general, but for the purpose of this project, I'm going to keep it simple and just kind of hard code a hitbox based on the location, because we only have one type of tile that can spawn leaves. So let's do something where we have self.leaf spawners equals that. And then we can do for tree, and this will be the tiles that we were returning before. We can do self.leaf spawners.append. And then for our hitbox, we'll do a pygame.rect, because if it's a rectangle, pygame.rect has a ton of useful functionality for that type of thing. So for that, we'll say for plus the tree's position on the x-axis, and then for plus the tree's position on the y-axis, 23 and 13. So you can go look at the dimensions of the tree image if you want. This is just taking the position of the tile and just kind of looking for the area of the tree image that it makes sense to spawn leaves. So we're actually offsetting it by 4 from the top left to the right, and then same thing down from the top left, because we don't want to start right in the top left, because that's technically air. So this is just the rectangle that makes sense for that image. You can go look at it and just draw it out if you wanted. So we can now print out this list, self.leaf spawners. And remember, the rect is x, y, width, height. Anyways, so we can print out our leaf spawners and close again. And we have our 2 rects here representing our 2 trees. Since we have our rects where the leaves can spawn now, we could theoretically easily pick locations to spawn the leaves, but now we need to be able to actually have the particles that we're spawning. So to do that, let's go ahead and make a new script. We'll call it particle.py. And this is a pretty basic one. So we'll do class particle def init, and then it needs access to the game. We can do self.game equals game. And then we want the particle type. We want the position. We want the velocity. We'll default that to 0, 0. We want the frame that we want it to start on. All right, so we can do self.type equals p-type, self.position equals list position. And remember, that list is just making a copy. All right, so, and then we can do self.velocity equals list velocity. And then self.animation equals self.game.assets. And then we'll take particle, and we'll have to load this in a moment. And then we'll take the particle type. And then we want a copy of that animation. And then self.animation.frame equals frame. All right, so that's the setup for our particle, because the particle needs to be able to move around, and it needs to have a velocity so that we can configure how it moves. And it has the animation, and that's really all you need. Well, also the type, obviously, but that's really all you need. Now we can just do def update self.position 0 plus equals the velocity. This is just the basic stuff, so we do the y-axis too. And then we need to do self.animation.update, and we'll do kill equals false if self.animation.notFrame done kill equals true. So our update function is going to do a couple things here. We'll return kill. It needs to determine when the particle needs to disappear, so that's what this kill variable is for. As soon as this update function returns true, that means that this particle needs to be removed. So we return true once the animation has finished playing, which was what we added before. This is a nice little utility attribute that we have for that. And we also have to update the animation in our update function and move the particle. So it does a couple things. If we wanted, we could add more behavior here as well, but it should be enough for now. And it's really important to remember the type of thing you're pulling from the assets here. Like for example, if this were a list of images, you'd probably have a problem, but we will be adding this in as an animation like we did for the player stuff. All right, so now we need one more function for a particle. We'll call it the render function. It needs a destination surface and an offset, and we'll take 0, 0, and we'll take image equals self.animation.image, and we just take that, and then we go surf.blit. We render our image onto the destination surf at the position we have, minus offset 0. And then this is something actually we're doing. I like to center my particles based on the center of the image instead of the top left. It just makes the behavior easier to work with and more aesthetically pleasing. So let's do minus image.getWidth, and then we divide that by 2. Now we can do self.position1 and just the whole thing for the y-axis. All right, so now we have the rendering coordinates for the x and the y-axis, and that should be sufficient for our rendering function. All right, so now we need to actually add our particle assets, and for that, we can go back to our assets thing right here and say particle/leaf. And that's the particle type we'll be using. If you remember, we said particle slash and then the type, and we'll be using leaf here. So we'll create an animation of load images, and then we'll do entities, particle leaf, I believe. Let's check that. So we go data, images, we have particles. So this will be particles/leaf. So we have 2 types in here. We'll be using just leaf for now. In here, there's 17 images. If you look in here, there's like different leaf images. Normally in my games, I would have the ability to recolor these, but right now we'll just be playing the animation and that's it. So it'll play through those leaf frames, which will load here and then attach to the particle. And then we'll have our particle as we wanted. So now that we have the particle object, I think it's time that we add our particle collection. So we can say self.particles equals that list. And if you remember, we had that return kill thing in the particle code. So in our loop here, we need to keep track of that and see if we need to remove it. So we'll do for particle in particles.copy. And again, we're doing the copy thing. We're doing the copy thing because we will be removing during iteration. So kill equals particle.update. So we're calling the particle.update, and then we're just checking if we need to kill it. So we can do if kill self.particles.remove particle, and that will handle that. We also want to render a particle, so particle.render, and then let's do self.display offset equals render scroll. All right. So we now have our collection of particles, and it should remove them as soon as the animation is played through. So now we just have to spawn our particles. So for that, let's look through our leaf spawners. So for rect in self.leaf spawners, if random.random, and this is going to be just a mess of numbers here, 49999 is less than rect.width by rect.height. I'm going to go import random here because we don't have that. Import random, and then we also want our particle. So from scripts.particle import particle. So if you're unaware, random.random is just a random number between 0 and 1. It's a floating point number, so it could be like 0.25 or something. And then we're just multiplying it by this and then checking it to see if it's less than the pixel area of our rectangle. So this is a way where you could have the spawn rate for leaves be proportional to the amount of pixels that hitbox covers, so that if you have like a bigger tree, it will spawn more leaves. And then this number right here is just to control the rate at which they spawn, because if you do this, it will spawn 100% of the time, like every single frame. So by multiplying it by that big number, it'll make it so it's not every frame. Anyways, if we've decided that this random odd chance has passed, then we can say our spawn position equals rect.x plus random.random by rect.width, and rect.y plus random by rect.height. And this is really one of the more interesting problems, I think, in this tutorial. It's just the spawning leaves problem. So there's a lot of random techniques you can pick up from here and different ways of solving problems. Of course, this doesn't generalize to that many different things. So there's just little things you could start thinking about here and there about how you would approach problems. Anyways, so we're taking the x of our rect and then adding the width multiplied by a random number from 0 to 1 times that. So that will give us any number that's within the bounds of the rect, because 1 times the width plus the left position will be the right position, and then 0 is the left. So anything in between is somewhere inside. And it's linearly distributed. So we can do self.particles.append, and this is where we spawn our particles. We do particle, and we do self to pass along the game. We want the leaf particle, and then we'll give it our position. So that will be position, that which we just calculated. We'll do for velocity. All the leaves will have the same velocity. You could randomize this if you wanted, if you want variance, but I'm going to leave it at -1.3 or -0.1 and 0.3. That will mean it's going slightly to the left, but mostly down, but also very slowly. For the frame to start on, we'll say random.randint. If you don't know, this is a random number within, I think it's inclusive of the two numbers we give it. So we'll give it 0 to 20. So that will select just a random frame for it to start on. So that way we don't always start with the biggest leaves. Anyways, so that will spawn our particles, and then this will manage our particles. So if we did everything right, it should work now. Aha, so you can see there are leaves falling now. They're a little bit rare, but as a visual effect they should be. Oh, I do see we have a problem though. So first of all, our leaves are kind of decaying into the 1 pixel dot very quickly, and then second of all, the animation is looping and they're not disappearing. So to deal with that, we need to go over to our animation here. And if you remember, we have a couple of options here for animation. So first of all, we need to make them decay slower. So we'll do image duration equals 20. So 20 frames for each frame of the animation. It's confusing terminology, but whatever. And then we want to disable the looping. So we'll do loop equals false. So we run that again. And we have leaves that are decaying much slower. It looks much nicer. And we're looking at this one on the bottom left, and the one, it just disappeared. So our leaves are disappearing. That's good. They're decaying slowly. That's good. So looks very nice. But there's one more effect I want to go ahead and add over here. So if we go over here into the particle management, we can add some extra rules for our particle. We already have our update function, but we could do something else if we wanted. So we can say if particle.type is leaf, then we can say particle.position 0 plus equals math.sign, particle.animation.frame by 0.035 by 0.3. All right, so we do need math. That's the math library that comes with Python, and that's just giving the sine function to us. So if you don't know what the sine function does, just think of a sine wave, so you know the curvy wave that goes up and down. You can just look up a picture if you want. And we're passing in just the animation's frame, so like the progress that we have in our animation. So if you know what the sine function does, it will give you a number between -1 and 1, and it will smoothly go between the two. If you were to plot it out, it would be a kind of a bit of a smooth curve. So it has a more natural pattern than just moving to the right at 1 pixel per second and moving to the left at 1 pixel per second. It will slow down as it gets to the edges. So what we're doing here is we're applying this random number that could be -1 or 1. Well, we're multiplying it by 0.3 to decrease the force of it. But we're applying that to the position. And because it's a number between -1 and 1, it actually sums up to 0 over time. So what this is doing in the short term is making the particle move back and forth, like right and left over time in just a smooth pattern. So this last part here, the 0.035 thing, is just to make sure that you don't go through a whole kind of loop of the sine function too fast. It's just to slow down how fast it goes left and right. And if you aren't aware, there's no limit to how big of a number you can put into the sine function. It will always give you a number between -1 and 1, so we don't have to worry about how far along that is. Anyways, if we were to run it again, we could see that our particles will move right and left now. So if you watch this particle closely, it'll like sway back and forth, right and left. So this is a technique I use for a lot of things. If you want natural animations for a variety of things, the sine wave is a really good way to get a natural look. You can layer it with some other stuff because technically it's a little bit too mathematically perfect, but it's more natural than the robotic multiplying, well, adding -1 or 1 technique. This is a lot smoother, but that's just a useful thing to keep in your toolbox. I recommend getting very comfortable with this function. If you just play around with it, you can get an idea of what it returns for different values, and you can get used to using it for things. Of course, it has tons of other applications in math as well, if you've taken trigonometry, but I won't get into that too much. So if we go back over here to the input code and take a look at our up arrow key, we'll see that we left it as you press up, the velocity of the player is just set to a negative number. So the effect of that is that if we run the game, you can just press up as much as you want and jump as much as you want. So normally in a game you wouldn't want this, maybe if you're playing Kirby, but for the most part, you don't want to be able to just jump to infinity. So what we'll be doing is we'll be adding some restrictions on jumping, and then also while we're at it, we'll add the wall slide effect so you can slide down a wall and then jump off of it. Alright, so let's get started with the easier part, which is the jumping aspect. So what I'm going to do is I'm going to go right here in this key up part and just swap this velocity change with player.jump, and then we'll fill out this jump function so that it handles the jump when the button's pressed. So we can just go over to our player here and we can add a new function. We'll go def jump self. We don't need any arguments. Alright, pass for now, and we need a couple of things added to the player to keep track of jumping. So we need self.jumps equals 1. The way I'll be doing this is that the player will have 1 jump, and a wall jump will consume that 1 jump, but if you run out of jumps and you're on a wall, you can still wall jump. So you can jump and then jump off of a wall, but if you fall and jump off of a wall, you can't jump again. That's just my preference for how this is implemented here. You could come up with all sorts of rules for how you want the jumping limits to work. If you want, you could just increase the maximum number of jumps to like 3 or something, so you can jump in the air 3 times. You can do all sorts of fun stuff. And I recommend you do play around with that if you want to get a good understanding of how this works. Anyways, so let's go over to this jump function. We'll need to keep track of this jumps attribute to determine whether or not jumps can be made. So let's do if self.jumps minus equals 1, self.velocity 1 equals -3, and self.error time equals 5. So we're doing a couple things here. First of all, we're reducing the jump count. So if our jump starts at 1 and we jump and reduce the number of jumps by 1, it'll go down to 0. And this statement will fail the next time you try to jump, because if jumps is 0, that evaluates to false, so you don't have any jumps left and you can't jump. Anyways, but it'll also modify the velocity, same as before, -3. And then while we're at it, we'll set the air time to 5. That's just to force it to automatically transition to the jump animation, because once the air time is above 4, it'll transition. Otherwise, you would have to wait like 4 frames, so you get a little bit of the running or idle animation before it actually switches to jump in the air, unless you have this line. Anyways, the next part is to actually restore your jumps after you've hit the ground, which is usually what you want to do, but I mean, you could make a mechanic where you have to maybe collect something in order to restore your jumps, and your jumps are a limited resource. But in our case, and with most games, you'll want to make it that when you touch the ground, you restore your jumps. So we'll do right here, when you collide with the floor going downwards, you can do self.jumps equals 1. And if you wanted to have 2 jumps, you could just swap these 2 numbers for 2, and that would make it so that you always have 2 jumps after each touch with the ground. Alright, so that's the basics of keeping track of your jumps. If we go over to the game, and if I press up twice, you'll see that I can only jump once. If I press the key loud enough, you might be able to hear it. But yeah, well, now if we go back over to here, we can go ahead and start working on the wall slide. So to do this, we'll add a attribute for, wall slide, and set it to false. Now this is where things get a little bit messy, because not only do we have to deal with the actual movement mechanics of dealing with a wall slide and the jumping resource management of a wall slide, but we also have to deal with the animation aspect of the wall slide. So there's a lot of components going on here. So this is going to be a bit more complicated than just the number of jumps that you have. So let's start by saying every single frame will say that self.wall slide equals false. And the purpose of this is so that this variable will act as a single frame switch, or like, I don't know, a button where it fires off an event once you press it. That's sort of how this is set up. So once you set it to true during the frame, it'll be true for the rest of that frame, but then when it comes back to here on the next update, it'll be false. So this is a useful trick if you want to have something that that's sort of an event that fires off once. So now we'll write the part where we'll determine if wall slide should be set to true. So we'll do if self.collisions right, or self.collisions left, and self.airtime is greater than 4, self.wall slide equals true. So what we're saying here is if we hit the wall on either side and we're in the air, and this is the threshold that we're using to determine if we should be showing the jump animation, but if we're in the air and we're touching a wall, then we should be sliding on that wall. So since we're using this technique where we basically set it to true and then switch it back to false every single frame, then we're basically saying only for the frames where this holds true will this be true. What you could also do is you could throw an else right here and say self.wall slide equals false, but this works as well. Now we can do self.velocity1 equals the minimum of self.velocity 1 and 0.5. So what we're doing here is we're capping the downward velocity at 0.5. Remember, the min function takes the lower of the two values, so if this number is lower than 0.5, it'll take it. If it's greater, it'll take 0.5, so that's just a 0.5 cap effectively. Now let's do if self.collisions right. So we need to break apart this statement here, because while this is the statement that determines if you're sliding on a wall, we need to break it down to determine which direction so that you can show the correct animation. Anyways, so we can just check if it's right, and if we know if it's not right, then it must be left, because that's how an OR statement works. Anyways, we can do self.flip equals false, and this is important for keeping our animation accurate, and then we can do else self.flip equals true. And remember, the base images for the player are facing right, which means that we want flip equals false when we're facing right, and then flip equals true for facing left. Anyways, now we want to do self.set action wall slide. And now the purpose of this wall slide variable, because if you think about it, we have most of the code here for handling the effects of the wall slide. So we're updating the animation, we're handling the flip, we're restricting the velocity. So this variable right here is just for a couple of things. It's used to prevent the animation set right here from being overridden by these ones. So we can go if not self.wall slide, because if you're sliding on the wall, you don't want it to switch to whatever the normal animation would be. And because of this restriction right here, it would technically be either you're in the jumping animation or wall slide, because this is the first case. But we can just break it all out and say, if we're wall sliding, don't do any of the other animations. We want to show the wall slide animation, which is whatever it was previously set to. And then once that becomes false, which will be as soon as you're no longer touching the wall, then it'll let it switch to the other animations again, which should probably be jump. Alright, so now that we have the animation side of things handled, and the slowly sliding down the wall side of things handled, we can go ahead and work on the jumping part of the wall slide. So we want to make it so you can jump off the wall. So we'll do this by doing if self.wall slide, and that's why we need this variable over here as well as an attribute. We'll do pass, and then this will become elif self.jumps, because we want to prioritize the wall slide first over the normal jumps. And then we'll say if self.flip and self.last movement 0 is less than 0, So what we're looking for is flip equals true, which means you're facing left, and your movement that you attempted to do is going to the left. Then self.velocity 0 equals 3.5. So that's going to add a velocity, almost like an impulse, pushing you to the right, which will push you away from the wall. And that's the jumping away from the wall part. So now the other part is the vertical component of the jump. So self.velocity 1 equals -2.5, and that will force you up. Same as the -3 here, except in a wall jump, you probably don't want to jump as high as a normal jump because you're also going to the side. Anyways, we'll do self.air time equals 5 just to get the animation updated. And we can do self.jumps equals max 0, self.jumps -1. So we want the jump to be consumed if you have one remaining by the wall jump. But like I said before, you should still be able to wall jump if you don't have any jumps left, which is why there's no check for the number of jumps you have before it gets to the statement. And then something you have to be careful about is because we're doing if self.jumps and not if self.jumps is greater than 0, then we have to make sure that the number of jumps can't go below 0. And technically, if you can wall jump when you have 0 jumps left, and you subtract 1 jump from there, it would go to -1. So that's a bit of a tricky bug that you don't want to deal with. So we max these two values so that the minimum value is 0. And that will effectively just only reduce your jump if you have them left. So now we need to deal with the other direction. So elif not self.flip and self.last movement 0 is greater than 0. And then we just kind of copy all of this, and there's better ways to do this, but this is good enough for now. And you just swap that direction on the x-axis, and that covers everything. All right, so that is our jump code. The last thing I'm going to do, and this is just for convenience if you want to add something on top of this, is I'll add a return true if the jump actually occurs, so that you could hook off some events from this jump function. So you could go over here and say if self.player.jump. So if the jump actually went through, then you could do something else. So normally in my games, I might add in a special animation for that, but I think I'll leave this for now. And you can go add that yourself if you want. Anyways, let's go back over to our update function. If you notice, we modify our velocity here in 2 dimensions. So we have our code for the gravity that runs up here in the entity parent class for the player. It will force the player to fall downwards and then cap it at 5. So that will make it so that if you're jumping up, it'll pull you down, and you've seen that already. But if you notice, we don't actually have any code for normalizing the x-axis. So if you were to jump off of a wall and have your velocity set right here to like -3.5, it would stay at that number and you would just constantly be moving left. And we don't want that. So to deal with that, we'll need to add some normalization to the horizontal velocity. And that just means that we're going to be making it move towards 0 so that it eventually gets to 0 and you stop being forced in that direction. Similar to how gravity will pull you down. You can think of this like air resistance. That's sort of what it's like, except technically we're exaggerating it for the sake of gameplay. So we'll do if self.velocity 0 is greater than 0, self.velocity 0 equals the minimum of self.velocity 0 minus 0.1 and 0. So what we're saying, actually said this should be max. So what we're saying here is that we want to subtract 0.1 from the velocity every frame if it's greater than 0, and then stop it from going below 0. So you just want to stop at 0. And then that will make it so that it brings it towards 0 if it's greater than 0. So we have to deal with the other side now, which is if the velocity is negative. So all that is you just take this, you copy it down here, you switch this to plus, and you switch this to a min. So that will make it so it'll take the two values and say which one is lower. So as soon as this number crosses 0 into the positive territory from these increases, it will get capped at 0 so that it can't actually go over. So this will just pull the number linearly towards 0, and that will give us the effect we're looking for. So if we go ahead and run our game now, we can run around, we can jump, and if we go over to wall, we can slide down it slowly. Oh, and we've got a crash here. So it appears that I have not added the last movement attribute. So that's just a simple concept. The idea is that you take whatever the previous movement was and do something based on that. So to add the last movement, we can just go over to our physics entity and we can say self.lastMovement equals 0, 0, because remember this is what we're inheriting from as the player, so it'll have access to everything in here. And then we can go over here and then copy this down into this update function, which takes the movement, and then we can just drop it right here and say that the last movement equals the movement. And now we should have this last movement attribute to work off of for our jump mechanic. And something important to note is that this movement variable is keeping track of movement, which is the input to the update, not the actual movement that was executed upon. So if, for example, you're running into a wall, it'll keep track of the intent to move towards that wall and not just put it as like 0 on the x-axis because you hit the wall. And that helps us keep track of the fact that we're actually trying to push up against that wall. Now if we run over to our game and we run it and we jump into a wall and we try to wall jump, it works properly. So it bounces us away. Jump up, bounce off the wall. Works as intended. So you can jump once and then you can jump off a wall, or if I go up to here and then slide down the wall and jump, that's our only jump. So that's how we intended for it to work, and it's working as intended. So these two things will cover pretty much all that we were looking for in terms of movement, at least in the jumping sliding space. There's one more thing that we have left for movement. Let's go ahead and add the dashing mechanic to the game. This is not only a movement ability, but it's also how you do the combat in this game. The enemies will shoot at you while you as the player have to beat them by dashing through them. So it serves multiple purposes. For the effect, we'll have to move the player suddenly, and we'll also have to have some nice visual effect to go along with it. So what I'll use is a burst of particles. So let's start by loading in the particles that we want to use. Let's grab the particle leaf. Let's copy that, and we'll say particle. And then for the image duration, we'll say 6 instead of 20, because this particle should not last nearly as long as the leaf. So if you look in our particles list, we do have this particle, which is just 4 images, and they're just circles. So I'm going to go ahead and close that though. So now that we have our particle animation loaded, we'll want to add the key binding for actually using the dash. So let's go down over to our keys here, and we'll do if event.key is pygame.kx, and that will be your key that we use to dash. We'll do player.dash or self.player.dash, and similar to the jump thing, that's something that we'll have to go ahead and add here. So let's go over to the player and we'll go under the jump code and we'll say def dash self. And this will be a pretty short function. We'll do if not self.dashing, which is what something else we'll need. Let's go up here and add it. Self.dashing equals 0. If not self.dashing, so self.dashing is 0, we can do if self.flip. So that's if you're facing left, self.dashing equals -60. And then we'll do else equals 60, and so that's if you're going right. So this dashing variable will keep track of how much we want to dash and in which direction. So 60 is how long we're going to dash for, and then this negative is for the direction. So you know how there's the idea that velocity is not only a speed, but also a direction? That's what we're using here. We're using that directional component to say which way we want to dash. So that's just a nice convenience that we can use. All right. So now we have to actually do something with this dashing variable. So we need to do something that says basically if it's not 0, then we need to apply the dashing effect. So for that, we can go up here into our update function. We can just go right here, I guess. It could go in a lot of different places here. So self.dashing is greater than 0. We'll do self.dashing equals max 0, self.dashing -1. And this should look familiar. That's the same thing we're doing right here. So this is just bringing it towards 0. So we need to manage our dashing value so that it just goes down towards 0 and that the effect can eventually end. So the other side of that's going to be the +1 with min. And then now we can do some other stuff. So what we'll say here is if the absolute of self.dashing is greater than 50, self.velocity 0 equals the absolute of self.dashing divided by self.dashing by 8. So what we're doing here is we're saying if we're in the first 10 frames of the dash, then we take this part, which is actually just, it's going to be 1 or -1, depending on which direction it is. So if you just divide the absolute by its own value, you'll get the direction of the scalar. So in our case, if it's a positive number, you'll get 1, -1 will be received when you have a negative number. And then that will just be multiplied by 8. So we're just modifying it based on the direction here. All right, so now we can do if self.dashing is 51, self.velocity 0 times equals 0.1. So what we're doing here is that at the end of these first 10 frames of our dash, we're going to severely cut down on our velocity. And this remaining velocity will be quickly just diminished by this code right here, which will reduce the velocity. So the purpose of this is just kind of cause a sudden stop to the dash. If you saw it from earlier, you dash suddenly, and then you stop, but there's a little bit of velocity left over. And that's how we can achieve that. So you might be wondering, okay, that's the first 10 frames, what are the last 54? So this is also not only working as our code for applying the dash, but it's also working as our cooldown code. So when this number is less than 50, but still greater than 0, if you remember, in order to dash, dashing has to go down to 0. So this is actually working as our cooldown, so that you can't dash as much as you want. So remember, this will eventually bring it to 0, but this is going to be 5/6 of a second before it goes completely to 0. So you have that little bit of time of a cooldown where you can't dash again. So you can't just dash as much as you want and basically fly around. So that's how we manage that. So I can run the game now and show you what this looks like. So I can run around, and if I press X, I can dash around, which is cool. Now it's time to add some visual effects to it. This just handles the movement component. And let's go over to entities here. Let's close this. If you remember, our physics entity up here has its own render function right here. So I want to make it so that when we dash, we turn invisible. And we just turn into kind of a stream of particles. So what we'll do is we'll take that render function and override it right here. We'll say def render, well, not override it, we're going to build on top of it. We'll take our surf and offset, and we'll do if the absolute of self.dashing is less than or equal to 50. So remember, this is accounting for both directions. You're saying if we're not in the first 10 frames of a dash, basically if the dash is on cooldown, or if it's just completely off of cooldown and we're not doing it at all, then we can go ahead and do super. So this is accessing the parent class and .render, and we'll pass in the surf and offset equals offset. So what we're doing here is we're kind of gating the rendering function of this physics entity, which we would normally be using, behind just an extra layer in the player that checks to see if we're dashing or not. And if we are dashing, then we don't want to actually render it, so it'll skip this, and it just won't show the player. All right, so that will make the player invisible. So the next part is the particles that I talked about earlier on. So for that, there's two sets of particles I want to do. So first, I want a burst of particles when you first start and when you end your dash. And then I want a stream of particles while you're dashing. So to do that, we can go ahead into our update function here. And right here, we can just add the code for particles. We can do self.game.particles.append. And this is where we can add a particle if we want. So for this, we need to actually have particles to work with. So let's go over up to the top, and we'll say from scripts.particle import particle. And while we're at it, I'm also going to grab the math module because we're going to be doing some trigonometry here. All right, so let's go back now that we have our imports done. we can work on spawning our particles for this. So like I said, we want a stream of particles just as the player's dashing. So for this, we can do particle, and then we'll pass in self.game, and we'll say it's a type particle, and we want to spawn it from self.rect. And if we go up here, that's this function here that generates the rect for the player. And we want to take the center of the rect, so this will just be a tuple, just the x and y coordinates of the center of the player. And that will be our spawn location. And then we also need actually, let's split this up here. So we'll say velocity equals, or I'll say p velocity just to distinguish it. So p velocity equals the math.cosine of an angle times a speed, and then we want the math.sine of an angle times the speed. And for this, we'll go ahead and say angle equals random.random by math.pi by 2, and our speed will be random.random by 0.5 plus 0.5. And then now we can take this p velocity here and say velocity equals p velocity, and then we'll also want frame equals random.random 0 to 7. All right, so what we're doing here is we're taking the cosine of a random angle. So well, first of all, let me import random real quick. So let's go import random. We're taking a random angle. This will be random.random times math.pi times 2, if you know how radians work. This is just the full circle of angles in radians. Like a full circle is math.pi times 2. And this random.random is just selecting a random angle within that full circle. If, for example, you were to just take times 10 or something, you would get it unevenly distributed because there's certain sections of the circle that show up more in the numbers 0 to 10 in radians than others. That's why you want the exact amount of math.pi times 2. Technically, if you were to just put in a really big number, it would be almost the same, but this is the technically correct way to do it. Anyways, so this will just get a random angle in a, like, think of a circle, just pointing in a random direction. And then we'll take a random speed, and this will be just a random number between 0.5 and 1. Because remember, random.random, 0 to 1. So you take that, multiply it by 0.5, and add 0.5, and you get 0.5 to 1. Alright, so for p velocity, we're taking the cosine of the angle times the speed, and the sine of the angle times the speed. The cosines for the x-axis, and the sines for the y-axis. This is a little bit of trigonometry. So what this is doing is it's generating a velocity based on the angle. And this is how you move something in a direction, in any case, pretty much. At least in 2D. In 3D, it's a bit more complicated. But in 2D, you take the cosine of the angle you want to move, and you multiply it by the amount you want to move for the x-axis. And then for the y-axis, it's the sine. And if you've taken any trigonometry, you would know about the whole opposite and adjacent sides of a triangle and their associations with the functions of cosine and sine. So there's actually math behind here if you've looked into trigonometry for how this all works, but it can get a lot more complicated than it needs to be. So you can actually just pretty much memorize this one statement right here, or this one formula, and this will get you through most of the trigonometry you need for games, in fact. I have a video about this topic as well if you want to get into it a bit, but this will cover most of what you need. The other half of what you need is using arctangent 2 to turn an x and y coordinate into an angle. So it's just the conversions between angles and Cartesian coordinates that represent vectors. Anyways, so you might be wondering, why would I go through all the effort to do all this trigonometry to generate a random direction to create our particle velocity with, instead of just picking an actually random velocity? So I've seen this in a lot of games, and I think I actually used to do this myself, where you just pick a random number for the x and y coordinates, and the problem with that is the way it's distributed and scaled. So for scaling, you run into the problem where if you're going diagonal, let's say you pick the random number from -1 to 1 for both of the axes. Let's say you go into the 1, 1 direction, so +1x, +1y, and that's your velocity. So that's moving twice as fast, if you think about it, because it's going diagonal, as if you were to go just straight right from getting 1 and 0 as your velocity. And the effect that creates visually is that if you spawn a ton of particles like that, it will create a weird explosion in the shape of a square instead of a circle. So that's the problem with the scaling. Technically, you could normalize those numbers using square roots and stuff in order to make it so that the scaling's correct and it is the shape of a circle, but then you still have problems with the way that it's distributed, like the way that particles get randomly distributed. So to do it correctly, if you want to spread something out in a circle, the best way to do it is to pick a random angle in polar coordinates and then convert that into Cartesian vectors for velocity. So that's a bit of math stuff, and it's really important to, at least when you get into more advanced topics in game development, if you want to make your stuff look natural and look good, a lot of times you do want to get into the math to make things look a little bit better than what the primitive solution might be. And that's just another random tip I'm dropping for you here. And actually, I've just noticed a rather large mistake I've made here. And this is just a side effect of how I'm making these tutorials. This whole section here is actually for the burst, and not for the stream. So if you remember, I said I want a stream of particles and a burst of particles. So technically, this part right here is the clause that's for the stream, so it's just anytime that you're in the middle of the actual movement of a dash that we would run this code. So for that, we'll actually want to take this, and we'll want to create another one of it modified for the stream. But since I just went and did all the math and explained that for the circle, I'm going to add the extra case for the circle here. So we'll do, so if ab self.dashing in 60, 50 for I in range 20, and this is what I was talking about when you do a bunch of particles. We'll say if our dashing is in 60, 50, this means if we're at the start or the end of our dash, we'll do this 20 times, we'll create 20 particles in random directions with random speeds, and that will be our burst. Alright, so now we can grab this and go ahead and fix the stream stuff over here. So that's going to be, we just drop it right here and boop. And same thing, except with some minor differences. So p velocity will have to be different this time. We'll do p velocity equals, and we'll say the absolute of player.dashing, or the absolute of self.dashing, divided by self.dashing by random.random by 3. So if you remember, an absolute divided by itself is just giving you the direction, 1 or -1, and then we just take the random number times 3, so it'll be just random number from 0 to 3 in the direction that we're dashing. So that way the stream of particles moves along with the movement a bit, instead of just staying stationary. And then we don't want any movement on the y-axis, because you dash on the x-axis, so we don't want that to be moving around. Anyways, so we'll keep everything else the same, and that should cover that other type of particles. So we have the stream particles, and we have our dashing particles right, or sorry, our burst of particles right here. So now if we go ahead and run the game again, we can run around. If we press X, oh, whoops, we're not supposed to have leaf. So that's a fun mistake you can make. We're supposed to swap this with particle. Wait a second, what's this game? That one's supposed to be leaf. This one's particle. Wait, why is that one? Aha! So if we go over to here, when I copied this at the beginning, I left that as loading from the leaf. So we want that to be actually particle, not leaf, and that should fix our dash. So if we go back over here, you can run around and you dash, and you get your start, you get your end burst and your line, but you don't get the start one, which is not intended. So to fix that, there's an important lesson to learn here, and that is that the order for some of these things does actually matter. So, if you think about it right here, we're setting it to 60 in our dash, and then say after a dash, we get to our update function at some point. So it goes through this update function, and we have our code here that adjusts our dash basically timer thing. So it'll go from 60 to 59 or negative 60 to negative 59. And by the time it gets down to here, but to this code, if it were set to 60, it would have been pulled away already, so it'd be at 59. So this is one of those situations where you can either take this code and move it up, like up here, or you can leave it as is and then change these numbers. Because technically this 50 for the end of the dash is also wrong. It would be 49 if it's right here. So I'm going to do the easy thing and just copy this and move it over here. I think it reads nicer to have the number 1650 as opposed to having to figure out why it's -1 in the future for some reason. So we can now dash, and we get both ends of our dash, which is great, and we have our line between just as we wanted it. And that should cover pretty much all of the movement stuff that we'll be doing, at least for the player. At this point, we have most of the base of the game done in terms of the movement and the basic implementations of the standard things you would find in a game like animations, particles, physics, etc. But it's time to turn our game into an actual game. And to do that, I think it would be fitting to have some enemies to fight. And the objective would be to defeat all the enemies and then move on to the next level without getting shot. Alright. So to start adding enemies, we'll do something very similar to the leaf spawners thing we have here. And we'll extract a different type of tile and use that to spawn things. So I'll demonstrate how you can add your own, I guess, spawners for the player and enemies. But then I'll quickly switch to using the pre-made levels I have because I don't want to sit here for an hour making levels. Alright, so first of all, let's extract some spawners, and then I'll go ahead and add them to the level data itself. So let's do for spawner in just like the tile, well, just like the leaf spawners, we'll do self.tilemap.extract, and then we'll do spawners 0 and spawners 1. Those will be the tile IDs we're looking for. And this time we don't want to use the whole keep thing, because keep is used to, well, keep the tile in the tile map. If we don't set keep to true, it will actually extract and remove the things that we're asking for. So we actually don't want these spawners to show up in our tile map. We want to just get the location so that we can put stuff there. And that way it works as a spawner as intended. So we'll do if spawner variant is 0. This will be the player spawner. We'll do self.player.position equals spawner position. And then else we'll just print out the position. Alright. And I'll say enemy. And then we can fill that in later. But for now, let's actually update our map here. So to do this, we can go back over to our level editor. Just go ahead and run this. And let's see if we actually have it in here. No, we don't. So we do need to load in the spawners. So if you look right here, we have decor, grass, large decor, and stone. If you go over to tiles, we have this extra one called spawners, which have a picture of the player and a picture of an enemy. So what we'll do here is we'll say spawners and then load images, and then we'll do tile/spawners. And that will give us what we need for that. Now if we run this again, we now have the player spawner. We can put it off grid, and we can drop one down there, and then we can go ahead and add a couple enemies as well. And I'll press O to save, and let's go ahead and run the game. Alright, so now spawned us in the right location, and if you look down here, it gives us the 2 locations of the enemies that we added. So with that, we can now actually spawn the enemies. To do that, we obviously need some enemies to spawn. So similar to the player, we're going to go over to entities, and we're going to add a new entity. All right, so let's add class enemy. and this will inherit from physics entity, same way the player does. And then we'll do definite game position size, all that good stuff. All right, and then we can do super dot init game enemy position size. All right, so with the enemy, we'll use the custom enemy animations, which are over here in entities enemy, and it has an idle animation and a run animation. So let's go ahead and load those in. So we can just do enemy slash idle animation, load images, entities slash enemy slash idle, and then we'll say image duration equals 6, similar to the player's idle animation, and then we'll also have an enemy run animation. We'll just swap these two idles for run, and then we'll set the duration to 4, similar to the player. All right, so now we can go back over here, and here's the idea for the enemies. They should be able to walk around, but then not walk off of the edge of an island. They should be able to turn around, and we just have a basic AI for just walking around kind of casually. And then it should also shoot at the player if that's appropriate. So that would be based on the location of the player, so whether or not the shot would line up. So the enemies will only be able to shoot horizontally. So it'll have to see if the player's within range and at the right level on the y-axis. But for the actual movement itself, it's going to be kind of like a Koopa. So if you've seen Koopas, they just walk back and forth, and then if they walk up to an edge, they'll turn around. So part of that pattern for AI is to keep track of whether or not it should be moving. So normally there's like a attribute or something that will keep track of whether or not it is moving and for how much longer it should be moving, and then you just randomly decide when it should be moving. Or you can have like a global timer where it's like if it's like you mod it by however many frames, and then you say if it's in this section of that modulo, then you're walking. So it could be a consistent pattern, but I would like the more random pattern, so we'll just use randomness in a timer. So that timer will be self.walking. And this will be similar to dashing in the sense that it's a timer, but this time we won't include direction because we'll derive it from the flip of the entity. All right, so the first step here is we'll do an def update self tile map movement equals 0, 0. And if you look at the player, these are the same arguments we have here. So if we want to do the physics movement and stuff, we'll need this super.update thing. So we can drop that in right here. So this is just calling the parent update function from physics entity, which handles the physics, as you know. We pass in the tile map and the movement we want to do. So we can modify the movement here to be whatever we want. So before we actually move, we should do some calculations to determine what we should be doing this frame. So we'll do if self.walking. We'll do a pass for now, and then we'll have an elif random.random is less than 0.01 self.walking equals random.randint 30 to 120. So what we're doing here is we're saying if we're walking, we have this space to do whatever we want, which we'll fill in later. And then otherwise, if we're not walking, basically, we can check if this random number is less than 0.01. Since random.random is random number between 0 and 1, that means that this has a 1 in 100 chance of occurring, which, since we're running at 60 FPS, that's 1 in every 1.67 seconds if we're not walking. So that's how long the average delay is before walking. And then our walking will be set to this random number, which is the number of frames we will continue to walk for. So that's random number between half a second to 2 seconds. All right, so from here, for the walking, we'll need to do a couple things. We'll start by making it so that it can just walk in one direction and that's it. We'll do movement equals movement 0 minus 0.5 if self.flip else 0.5 movement. So what we're doing here is we're saying that we want to subtract 0.5 if we're flipped, that's facing left, or otherwise we want to add 0.5. So if movement's just given as 0, because that's what the keyword is, then it'll be negative 0.5 or 0.5 depending on what the flip is and if we're walking. And then it'll just keep whatever the y-axis movement was. Now, the next step here is to take the walking thing and reduce the timer. So walking equals max 0, self.walking, you've seen this before, -1. So that'll just cut it down to 0 over time, if we're walking. So let's go ahead and actually spawn our enemies. To do that, we'll have to go ahead and import our enemies, and then we'll need to go over to our spawn code right here, and we'll say we want an enemy with the game. We want to give it the spawner's position to place it, and then we'll say it's 8 by 15. You can look at the image yourself and go compute what the dimension should be, but I'm just writing it down here since it's not actually teaching you much. All right, so we also want a self.enemies to add this to. So we'll do self.enemies.append, and we'll add in the enemy. So now with our list of enemies, we need to render them. So I would like them to be right after the tile map, but also still before the player. So we'll do for enemy in self.enemies.copy, because we're going to be removing from that later. We'll do enemy.update. This is the same update code from before. And then we'll give it a default movement of 0, 0. And then we want to do enemy.render, and we'll give it self.display, and the offset will be the render scroll. All right, if we run this, you can see that they're up there and they're walking around. It should walk off the edge because we have, well, yep, they can walk off the edge, and that's what we want to fix. All right, so to do that, let's go ahead and go back to our enemies here. And we want to say, if there's a solid tile in front of where you're walking to and below, meaning that you're about to walk onto a floor, you can keep walking. Otherwise, you need to turn around. So to do that, we need to add some case right here under if self.walking. But we also need some way to determine if there's a solid tile like right in front of it. So to do that, we'll go ahead and head back to our tile map, and we'll add, I think, what's going to be the last function for this video. So let's add a def solid check. So this is just checking for a solid tile, and we'll give it a position. It will compute the tile location as the string of the int of the position 0. We've been through this before. Self.tile size plus semicolon plus string int position 1 self.tile size, and that will give us the tile location. If you remember, this is just converting our pixels into the coordinates of the grid system, because we were looking up tiles that you can collide with, which have to be on the grid. All right, so we can do if tile location in self.tilemap, if self.tilemap tile location, type in physics tiles, return self.tilemap tile location. All right, so we're looking to see if this location exists, and then if this is a physics tile, which we have defined up here. So there's two types of physics tiles. We have grass and stone. Those are the things you can actually collide with. So we want to see if it exists, and if it's a physics tile, then we return that tile data. In our case, we're not going to actually use the tile data for anything. We're just going to check if it exists, because if it doesn't hit this line, then it'll return none. So we can just put this behind an if statement. Since none evaluates to false, as a Boolean, this will be either true or false, depending on whether or not something was found. So we can go ahead and use this function now. We can head back over to our entities. And right here we can add that special case I was talking about. So we'll have if tile map, remember we have it passed in right here, which is convenient, dot solid check, and we'll do self.rect center x. And this is where the math gets a little bit funky. We're using some magic numbers and stuff. It's based on the movement. So remember we have this -5 positive, well, -0.5 positive 0.5 depending on flip. We're doing the same thing here, except it's more extreme. We're looking 7 pixels to the left or to the right based on the flip. And that's from the center. And then the next step is to take the self.position 1 plus 23. So that will be below the player in the ground. So this is just kind of scanning out in front of wherever you're facing and then into the ground. And it's taking this location and looking to see if there is a tile there. Now, we have this as an if statement, and if it evaluates it true, that means there's a solid tile, and that we should be able to move. Otherwise, this will do self.flip equals not self.flip. So you just flip it around if there's not a tile there. The side effect of this is that depending on how far you're looking ahead and the tile size and stuff, it could theoretically end up in a situation where you're standing on a tile and just flipping back and forth constantly because there's nothing on either side. So you do have to be careful about that stuff. It's good to think about what your environment is when you're doing these types of things. Like, for example, right now, we have the code for not walking off the edge and turning around when it gets to the edge, but we don't have anything for if it hits a wall to turn around. I can write that up here in a moment, but I don't believe, yeah, they're both on a flat surface where they would walk down as opposed to up, and there's no walls for them to run into. So this is not the greatest example of running into walls, but all we have to do for the walls part is just take this part right here, just grab this, we say if that, and walking, you can drop it right here. If that's the case, then you just do the flip. So we're saying if you run into something on your right or your left, you turn around while you're walking if the solid check passes. Otherwise, you can walk. There's better ways to close this so you don't have to indent it as far, but I'm not going to bother with that. Anyways, that should handle the movement. So let's get into the animations here. So we'll do, this is pretty simple. If movement 0 does not equal 0, self.set action run, because you're moving, so you're running, else self.set action idle. And that's as simple as it is. So if you're not moving, set it's idle. This is a lot simpler than the player's animations because it doesn't have jump or stuff like that. So now you can see that they're walking around and stuff. And they turn around when they get to the edge, which is nice. And they kind of walk for random durations and pause for a bit, which is exactly what we wanted. All right. So the next part is to give them a gun so that they can shoot at us. So I'll go to entities again. And for this, we'll need to modify our render function for the enemy so that we can draw a gun on top of it. So to do that, we'll do def render self surf offset equals 0, 0. So this is like we have down here for the player, except instead of hiding it behind something so we can turn invisible, we're just going to take this as is and call the parent function for the rendering. So this is effectively the exact same as not having that function at all. But we're going to add in some extra stuff here because we want to show the gun. So we'll have if self.flip pass else pass. So the gun will need to be able to flip depending on which direction the player is facing. Let's go back over to game and load in the gun. So we do gun, load image, gun.png. It's as simple as that. And then we go back to entities. And we can render this gun image on top of the player. So we'll do surf.bullet. And this is where we're going to have to handle the flipping. Because so if self.flip, that means the gun should also be flipped as well. Because if you're facing left, then the player image is flipped. So since the gun image is facing right by default, we also need to flip that so it's facing left. So we'll do pygame.transform.flip. You've seen this before. Self.game.assets gun, and then we'll say true on the x-axis, false for the y-axis. So this is flipping on the x-axis. We'll do self.rect.centerx -4. This part is just to offset the gun so that it's put in the right spot. You can play around with this number to visually see how it changes. It's just moving it by 4 pixels. And there's just a specific spot I want this placed at. And then we'll do minus self.assets gun.getWidth. That's just accounting for the width of the gun image, because we want to render this from the perspective of the top right of the gun image when the gun is facing left, and the top left when it's facing right. So subtracting the width accounts for that. This is another thing we should just kind of play with the numbers and see what you get so you understand. And then So this last part is the offset of the camera. So this is the same thing used on the player's rendering as well. And then we can do the y-axis, which is rect.center y, and we don't touch this, we'll just do offset -1, so we don't want any funny offsets there. This is a 188 character line of code, so this is a bit long. Remember, if you get lost on this, go ahead and check out the reference files in the description. So the other side's a bit easier because we had to do special math to deal with the flip, plus the actual flip transformation in there. So we'll do something a lot simpler for this one. So surf.blit self.game.assets gun and self.rect.center x +4. So this is the other direction, so we want +4 instead of -4. Minus offset 0, that's the camera, self.rect 0 rect.center y minus offset 1. Alright, so this is much simpler. It's the center with just a 4-pixel offset and the camera. And that should render our gun. That was a bit hectic, but here we go. Oops, I must have written self.assets somewhere. Where did I do that? Ah, yes. This should be self.game.assets. Alright, so I run it, and they're holding guns. If you notice, the guns are held out in front of the enemies. They're floating for now, but it'll look a little bit better when we add the outlines later. And they're a bit small, but that's because it's pixel art. In proportion to the player, they're probably the correct size. It's just a small aesthetic thing that we wanted to tack on. Now, the next step is to make these guns shoot. So, the way this is going to work is that not that we have a gun object that can shoot, but instead we're going to make it so that the enemy renders the gun image and then also generates the bullets. Before we can actually have our projectiles, we need to create something for them to be stored in the game itself. We also need the image for the projectiles. So for this, we can just